Questions about stereochemistry? Okay, guys, carbohydrates. Carbohydrates you'll see in biochemistry. Carbohydrates can be shown in open chain form or ring form. Open chain form will be shown as a Fischer projection. Okay? And you have more than one. Okay? Glyceraldehyde has one chiral carbon. These two guys have two chiral carbons. Okay? And then three. So we can just show the crosshairs like that. By the way, these two carbohydrates are called erythros and threose. That's where the term erythro comes from, because erythros, the two OHs are on the same side. But in threose, the two OHs are on opposite sides of the Fischer projection. So that's where those two terms comes from. Your 6-carbon carbohydrates, probably the most common, including glucose. These are shown below. Glucose has a certain configuration of the 4 chiral carbons. And then you could have the mirror image of it. What's the relationship between these compounds here? For example, these first two, allose and altrose. What's the relationship between the two? Diastereomers. The mirror image of all 4 on that side would be all 4 on this side. Well, that ain't that, as long as the backbone's the same. Yeah. Are they stereoisomers? Yes. You have the same connectivity. That's the same. This is the same connectivity. It's just right here. The only difference is this first carbon here, the first chiral carbon. If you switch in the Fischer projection, you're changing R to S. I don't know what that is, but if that's R, that's S. These 3 are the same. The mirror image of, again, this would be all over here. Not the mirror image, but it is a stereoisomer. So what's the relationship? Diastereomers, yes. These are all diastereomers of each other. Okay. In going from here to here, only one chiral carbon has changed. That one. When only one changes, and you have many, that's called an epimer. Okay? So these two are epimers. Epimer is a specific or a type of diastereomer where only one chiral center has changed. Allose and glucose, are they epimers? Yes, they are, because only that one chiral carbon has changed. The other 3 are the same. How about allose and mannose? Are they epimers? No, 2 chiral carbons have changed. The first 2 have changed. That's more than 1. So they would not be epimers. You can also use a designation. Mannose is the C2 epimer of glucose. C2. Worry about that. It's because, hold on, let's look at this example here. C2 epimers. That's the first carbon, C1. C2. C2 is where the change took place. The rest is the same. So we can call these C2 epimers. It gives us terminology we can use to talk about the relationship between these 2 compounds. Okay? C3 epimers. Okay. You will see carbohydrates in biochem. Back to the pink sheet, yeah. Diastereomers, we've done, yeah. Epimers, yeah. Question, just to clarify. What's the enantiomer of a compound that has 4 chiral carbons and the 4 are RRSR? What would be the enantiomer? The enantiomer of RRSR is what? SSRS. When you look in the mirror, everything is changed. All your configurations are reversed or changed. What would be a diastereomer of the one underlying? Many possibilities. All R would be a diastereomer, right? What if I showed you the same compound, but it was RRRR? It'd be a diastereomer. That would also be an epimer because there's only one difference from the original, right? Miso compound, we said what that was. A miso compound is a compound that, even though it has chiral carbons, it's not chiral as a whole. It's not a chiral compound because it has a plane of symmetry. And that was what we saw in the previous compound when the 2n+2 formula told us there would be 4 max stereoisomers, but it ended up being only 3. We drew 4 on the board, but 2 of them ended up being the same thing. So there was really only 3 on the board. That one compound is called a Miso compound. It was the same thing because it had a plane of symmetry, and thus the mirror image is the same thing. But it did have chiral carbons. We call such a compound Miso. Okay, finding Waldo. That basically means finding a plane of symmetry. We'll look at that on the other page. Before we move there, let's look over here. We need to get back to reactions, and this applies stereochemistry to reactions. So these are the types of questions you could be asked right below this reaction. Here. Regioselective versus stereoselective. You can be looking at this, and this is one where I highly recommend you first turn the alkene. When you need to turn it, I think in my recommendation up here it kind of clarifies that. Whenever the 2 carbons of the alkene are prochiral. What does pro mean? No, I don't think it means likes you. What is pro? You see that in biology.
In favor of?
No, unless I'm wrong. Pro eukaryotic or something? First, I think it means originates, original or something, or leads to genesis. Basically, these are prochiral. They become chiral. Pro-eukaryotic, it eventually became eukaryotic, I think, but pro is the original. Sort of like that. These become chiral. Unless you hydrogenate. But in this reaction here, I mean, even if you were just doing Br2, just look at this. Boom, 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 boom. If we put a bromine here and a bromine here, that is, we just brominated it like in lab, Br2, bromine to each carbon. Well, look, now each carbon of the alkene is chiral. Does everybody agree? Is that a chiral carbon? Yes. Is that? Yes. You see how they're now both chiral? That's what we mean by that. These 2 carbons are both prochiral. Now that's ICL. With ICL, you got regiochemistry. Which carbon's the iodine going to end up on? Which carbon's the Cl going to end up on? I don't know. I'll just randomly put one here, but we're going to end up with iodine on one and a Cl on the other. Again, but both are chiral. When they're both chiral, that's when we really have to look at this closer. And I recommended you turn this guy. Right now it's on the board like this. Okay, thumb down. Turn it like this, and now the thumb is either forward or back. Okay? The thing's down, so we turn this. I'm also going to draw the alkene just straight like this. Isopropyl and the methyl, we can both show them back. And this isopropyl, which is trans to that isopropyl, we can show it forward here. And so if you turn this first and then do your reactions, to me it's going to be a lot easier, because just by turning it, you're already set your stereochemistry. And then the new bonds, you put them in the plane, either straight up or straight down. Because now the alkene, I've turned it, it either reacts from the top or the bottom. The reaction takes place from the top or the bottom. Okay? I turned it, some groups are now forward, so isopropyl's forward, reaction here or here, straight up or straight down. Please look at that. Okay, we'll probably do that next time. That's sort of pulling everything together there and answering questions like regioselective and antioselective. When drawn, is your product a retro or 3O? Okay? Lots of questions there. We'll skip below here. I didn't mention on the carbohydrate handout, but you may notice capital DL versus little dl. Rotation of PP light, that's little dl. That's our definition. Okay? Early on, there was a second definition of DL established. That's based on glyceraldehyde, which is the first carbohydrate on that page. And all carbohydrates that come from glyceraldehyde or D-glyceraldehyde are called D-carbohydrates. That was an old definition. Anytime that is used, it's going to be a capital DL. Okay, that means something else. That was listed on the carbohydrate page. Optical activity, rotating plus or minus, that's little dl. Okay? They're not the same, but the optical activity is the little dl. All right? These are not the same, because some D carbohydrates actually rotate to the left, meaning they would be L. Okay? Not the same. Two different definitions or uses of DL. Resolution of enantiomers by conversion to diastereomeric salts. Let's look at that real quick. Resolution of enantiomers, resolving, separating enantiomers. We've not talked about this before. How do you separate enantiomers? If you think about it, they have the same physical properties. So can you separate them by distillation? No, they have the same boiling point. Can you separate them by recrystallization? No, they have the same solubility, so why would one crystallize and one stay dissolved? You can't expect that. They have the same solubility. So usually when you separate things, you're taking advantage of their physical properties, and you're designing an experiment to get one to do something based on a physical property and the other to not, and you leave it separated. So how do you separate enantiomers? Well, it can be difficult. That's why it's cheaper to make for a drug to be racemic, 50-50 mix. To separate those and to only have a drug being only like R or something, that's going to cost more money and more science and more, etc. Here's one way to separate enantiomers, using a chiral resolving agent. What if you have an RS mix, 50-50 mix, or some mix? One way we can do is we can react that with something that is just S, for example. And the S enantiomer will react with S, and basically we're joining together here in this generic reaction. SS would react to make an SS compound, where R and S reacts to make an RS compound. Now consider the relationship between RS and SS. What's the relationship? What's the relationship between these two compounds, now that they're joined together like this? Now diastereomers, because the mirror image of RS is SR, and that's not the mirror image. Okay, we're talking about stereoisomers. Now we have diastereomers after this reaction. And diastereomers have different physical properties. Now you can potentially separate these two much easier. Now, sometimes diastereomers have very similar properties because they are stereoisomers. But sometimes they have very different properties. So this can vary, and you try to get one where these two have pretty different properties. And now maybe you can separate them by recrystallization. And that's what this example is showing. Now, in this example, and in most examples, the reaction we're doing up here is making a salt by an acid-base reaction. Let's look at a specific here. Tartaric acid. I'm sorry, actually the amine. The amine is racemic, plus minus, DL. Okay? One chiral carbon, let's consider we have racemic, 50-50 mix of the two enantiomers. How can we separate them? In this example, we react with tartaric acid, which is just one enantiomer. By the way, how do you get tartaric acid as one enantiomer? How did you separate it? Well, guess what? Tartaric acid, this enantiomer comes from nature. It's in grapes. And nature can give us just one enantiomer. So you can get this as one enantiomer. This is a base. This is an acid. It's actually a diacid. And we can react these together. The base takes the H, leaving behind the anion. And now we have a salt. But we have two different salts. This one is RRR, where this one down here is SRR. Because remember, the amine we had R and S. These are both RR. That's plus, so that's what? D? The D enantiomer is RR. Now, these are not covalently bound. They're ionically attracting. But this is still considered one compound, and it behaves as one compound. That was RRR, this was SRR. What's the relationship between the two in the circle? Diastereomers, right? R. Everything has the same conductivity. That's not the mirror image. The mirror image would be SSS. Not. These are diastereomers. These salts have different properties. And in this scenario, the two salts will crystallize differently. And you'll have to read this, but I believe the B, which one was B, the bottom one? The B salt will crystallize. It'll give crystals from a certain solvent, where the other one will just stay dissolved. And you can get crystals of the B, and you've separated it from the A. Then you take these crystals and you can regenerate this. This nitrogen has a proton on it. How do you go back to neutral? You need to remove the proton. What will remove the proton? A base. React with the base, remove the proton, and now you have this. But it's only S. Now that'll be just washed out. That's now ionic. You can separate this from the ions. And now you have the S amine, where at the beginning we started with the mixture, 50-50 mixture. So, making a diastereomer, separating then, and then regenerating the neutral if you want the neutral. Naproxen sodium, the drug you just did polarimetry of, it's supposed to be one enantiomer. Okay? How does the drug company separate the two enantiomers? The same type of way. They make a salt. Finding the right salt, though, takes a lot of research. A lot of trial and error. Okay, let's see where we're at. History of chirality on the back. Okay, where's Waldo? Number 7 there. Where's Waldo? I sent out a key to this, but hopefully you're not looking at the key until you have tried the problem, struggled with them, ask me like a number of you have been doing. Any questions about the top? I did send out a key to the top, but any questions about those? How we do on the top ones up there? What about these up here? How we do on these? Any questions about these? Good to go on all those? Nobody had a question about this one? So the Fischer projection with film on top and up on the bottom, is it a retro trio? Let's look down here. Waldo. Identify each of the following as chiral, achiral, or Miso. First one, chiral or achiral? Carol, anybody else? Why Carol?
Each of the carbons that are attached to the bromine have 4 substituents, and
Yes, that's a chiral carbon. Yes, that's a chiral carbon. Yeah.
And there is no planar symmetry.
No planar symmetry.
So,
Ultimately, how do you tell if a compound's chiral? Doesn't have a planar symmetry. Is that chiral? No, it has a planar symmetry. That means the mirror image is the same thing. Now, there's ways to tell. I show you a compound. I tell you, you see it's got 1 chiral carbon. Okay, does the compound have a planar symmetry? Compound with one chiral carbon, will the compound have a plane of symmetry? No, we said that a compound with one chiral carbon that one carbon will ruin the plane of symmetry for the whole compound. A compound with one chiral carbon is going to be chiral. What if it had two? Is it going to be chiral? We showed an example of one with two, yet it was not chiral. It was called a Miso compound. Okay? If it has two, it may, because it's possible to have a mirror plane with two. Well, what about 3, 4, 5, 6, or 7? On and on. Okay? Does this have a plane of symmetry? Basically, where's Waldo? That's what we're playing here. Is there a plane of symmetry? Can you find planes of symmetry? Plane of symmetry here. Is that a plane of symmetry? Obviously not. There's not two bromines on the other side. How about here? Is that a plane of symmetry? No. Bromine 4 needs a bromine 4. Not a plane of symmetry. I don't see one. So what's the answer? Compound is chiral. Okay? That is, if we drew the compound with that one bolded and this one dashed, what's the relationship between these two compounds? Enantiomers. Will those superimpose? Not if they're enantiomers, they won't. Yes, these are enantiomers. These will not superimpose. By the way, is this compound cis or trans? Trans. How about this one? Trans. They're both trans. They're enantiomers of each other. The mirror image of trans is trans. You see my mirror image? I'm trans. No. There you go. Yeah. Oh, okay. Right? You're mirroring me, right? I'm trans and you are. Okay. Now I'm cis. Now you're cis. Mirror image of cis is cis, right? If you ever look in the mirror like this and you're let me know. It ain't gonna be that way. Where did we first see this at? Don't pull this out, but remember back over here? Ring, cyclohex. Right here. I mean, two bromines, two methyls is the same thing. Remember we introduced trans? And I said these are different compounds, just like your left hand and your right is different. See, we didn't know anything about this at that point. But it was in your notes. See? These are enantiomers. They're different compounds. How about these two? Same or different? Well, just look at this. Is this compound chiral? No, because I found Waldo. There's a plane of symmetry right there. So what does it tell us about the mirror image? First off, is this the mirror image? Yes, because all centers switched. It is. I didn't draw it as a mirror image, but it is. That's the mirror image. But is it the same or different? Same. Because something with a plane of symmetry in the mirror image is the same thing. So you don't have to worry about moving it or anything. You just use these sort of rules that I'm trying to tell you here. Of course, this one is just like the next one on the page. Right? Just like this. This is achiral. With A meaning not, right? I'm sure there's some term in biology. Asymmetric. Aprotic, meaning non-protic. Achiral, non-chiral. Is there a question?
So what's the difference between achiral and
Miso? Miso is a specific type of achiral compound. Okay, well I should have probably labeled this as Miso, thank you. It is achiral, but it's also Miso. And I said or, so it's almost like these are different. It's very close. You just have to ask for clarification, like you did. What is Miso? Miso is an achiral compound that has chiral carbons. Does this compound have chiral carbons? Yes, it does. If you look at it, it has 2. But it's not chiral as a whole because it has a plane of symmetry. We call that Miso. This is a little vague in the way this is worded. I mean, I could call that Miso, then you'd be like, well, is it not achiral? Yes, it's achiral. The difference is, what about water? Is it chiral? Or let's stick to carbon, because that might confuse you. It's so simple. Things that are so simple. Okay, is that chiral? No, it's achiral. Is that Miso? You wouldn't call it Miso either, because a Miso compound has chiral carbons. Miso is a specific. We would just call that achiral. I'm calling this Miso because it's both achiral and Miso. Let's keep on. Maybe that'll clear it up some. Here we go. Chiral, achiral, what? Chiral. No plane of symmetry. Okay? No plane of symmetry here. Yes, trust that. It's either going to be there or not here. This is chiral. Mirror image will be different. Okay, uh-oh, these 2. 3. Somebody got the first one here? Somebody got the first one? You got a working method to get this? Want to do a Fischer projection? I think Fischer projections help.
I was saying, could you rotate it to make it like be achiral if you want? Or like the way it's written, obviously you can't just draw a line, make a plane symmetry, but if you like took and twisted.
Well, is that a plane of symmetry right there? You got chlorine on one side, chlorine on the other. You got methyl on one side, methyl on the other. I can't tell that way. It's not drawn in a good way for me to see it. I would recommend a Fischer projection. That's why I tried to teach you how to do Fischer projections and told you that's the power of the Fischer projection. Let's draw another Fischer projection. Okay? We've got 2 chiral carbons. Yes, we do. We also have 4 total carbons. 1, 2, 3, 4. Typically in the Fischer projection, your carbons are straight up and down. We've got 2 chiral carbons. This is a classical 2 crosshairs. Methyl at top and methyl at bottom. That's methyl 1, that's methyl 4. Or carbon 1, carbon 4. I'm going to label these as, that is methyl 1, this is carbon 4. That way, carbon 1 is up, carbon 4 is by the ground. Everybody agree? There's 4, there's the ground. 4 is closer to the ground. Thus, this is the ground. Standing on the ground, I'm going to look at the first chiral carbon. The thing in the plane going away. With the chlorine going away, what side's the methyl on? Chlorine going away, methyl's on my right. It's going back, right? Uh-oh. I got to draw it like this. With chlorine going away, methyl's on the right. H is on the left. There's an undrawn H here. Okay, let's come over here. With chlorine going away, what side's methyl 4 on? With the other chlorine going away, the methyl's on the right. Yes. H here. That's how I see it. Now, for this purpose, we don't have to put the chlorine at the top and bottom. But what I want to show you here is you can rotate Fischers. By the way, we're done right here. We are done. Okay? Because now, what do you see here? Just look at this structure. What do you see? Everybody see it now? Bam. Done. put it in Fischer, and the light comes on, right? Everybody see that? Okay. So what's the answer here? What's the answer? Miso. It's achiral, but it's got chiral carbons. Miso. And the power of the Fischer projection, yeah? What if we were told to draw this compound in the Fischer with methyls at top and bottom? I would have did this first. Then you can rotate it. These three will just rotate like a dial. Okay? I'm holding this bond here. Here's the three down here. Let's make chlorine, by the way, going towards you or back? Yeah. Let's make blue chlorine. I'll put the methyl over here to make it just like that. Chlorine going back, methyl over there, a little H over here. Both of these coming forward. But see, these three will just spin like this. You see that? And so if the chlorine's back, if I put the methyl down, it's now down, but it's going back if it's down. What side would the chlorine now be on? It'll be over here. This spinning is just like this spinning. That is, if I move the methyl here, the chlorine will go here, and the H will go here. Again, I tried to show you here, but on the board, it's just like this or like this. I'm going to just move this down. The methyl comes here, the chlorine comes here, and the H goes over there. Finish up on the top. What side's the chlorine on the top? Correct. Because the methyl goes up here, this just spins. Chlorine here, H here. But again, you see the plane of symmetry. But now we have methyls at top and bottom in case you were asked to draw it like that. Let's do the next one. By the way, let me tell you a little trick. Anybody want to know a trick? Not really a trick, it's just more information. So ultimately we said that is a plane of symmetry right there, right? We just can't see it as drawn because it's like this. If that's a plane of symmetry, that means that these two chiral carbons are mirroring each other. A mirror plane. Let's do R and S over here. The H is coming forward. Chlorine's 1. Carbon with chlorine would be 2. Methyl would be 3. H coming forward. Counterclockwise, but the H is coming forward, so what is this? R. Okay, real quick, what's the other one?
S.
Over here?
Yes.
S, how do you know? Because each side is mirroring. And the mirror image of R is what? S. I'll bet you a steak dinner the other one's S. Because we've already identified that it is a mirror plane. So it has to be S if it's a mirror plane. Because the mirror image of R is S. Okay? So if you kind of start by doing that, you can kind of get the answer that way. Over here. Well, once you do those two on your own, after you see we do them, let's look below in some rings. Chiral, achiral, Miso, what do we get? Where's Waldo? Mirror plane? Yes, there's a mirror plane right through here. See it? Half a chlorine forward, mirroring half a chlorine forward. Half a ring, half a ring. Half a bromine back, mirroring half a bromine back. That's a mirror plane. Since it has a mirror plane, what's the answer? Achiral. This compound is not Miso. Why is it not Miso? It doesn't even have chiral carbons. That carbon is not chiral. Because if you go this way, you get the same as if you go this way. So you wouldn't call that Miso. Everybody with me? Victoria?
How come it wouldn't be, how come, what is it called? The third cyclopentane on top would be considered chiral, but this one would not be considered chiral? The one that you just drew on the board.
The third one?
No, the one you just drew on the board. How come that wouldn't be considered chiral? Because I thought it wasn't possible to do a plane of symmetry.
I'm lost. This one?
No, the one you did on the board, the one that you just labeled achiral. I thought it wasn't possible to do a plane of symmetry diagonal because they're both different kinds.
Amelia?
I'm confused as to why the one that you just drew on the board is achiral because I thought it's not possible to do a plane of symmetry through that through those two atoms because they're different.
Well, are you saying that's not a plane of symmetry? This is cutting right through a chlorine. You got a half a chlorine coming forward, mirroring a half a chlorine coming forward. Half a ring, half a bromine back, half a bromine back. It is a plane of symmetry. I'm not sure what your difficulty is. Do you not believe that that's a plane of symmetry?
I didn't believe it was.
You don't think it is? I mean, one side of the line is the same as the other side of the line, and they're mirroring. You need to look at it and see that. I mean, I'm not going to be able to explain it to you right here. We can look at it again, but it is a plane of symmetry. I'm also not quite certain of what else you said about it. So, ask me again. Over here, chiral, basically we're playing Where's Waldo? Do you see Waldo?
No.
I mean, the only way a bromine is going to mirror a bromine unless you cut, I mean, you can't cut right through that one. There's got to be a bromine over here. These are mirroring, but you need a methyl here to mirror that. There's no plane of symmetry. But it does have chiral carbons. I mean, that's a chiral carbon and that's a chiral carbon. It's Miso. No, I'm sorry. It's not Miso. There's no plane of symmetry. It is chiral. This one was achiral. Right? Over here. Where's Waldo? Got two planes of symmetry. One plane of symmetry is right through here. The other plane of symmetry is right through there. There's no chiral carbons. It's achiral. That guy has two planes of symmetry. Okay, you can do that one on your own. This is a 5-membered ring. Sometimes you may see rings drawn like this. If you get good, you can see these, but it may be difficult at the beginning. Anybody see something here? Where's Waldo? See a plane of symmetry? It does have a plane of symmetry. The plane, I'm not good at drawing this, but it cuts right through that carbon and right through these two. One way you can do is redraw this. It's a 5-membered ring. Are these bromines cis or trans, do you think, how this is drawn? Yeah, they're both up. Okay? We're taking some liberties here. It's not good bond angles, but it's a 5-membered ring. Okay, the name of this compound is 1,2-dibromocyclopentane, but it would be cis. You could also have trans. We can redraw this. Sort of like that. Is that the same compound just redrawn? Yeah. And now we see what I tried to show you there, right through that carbon in between these two. Okay? Now this compound may be drawn a little bit differently and maybe more better. Or better, that's slang for better. This is cis, and so maybe we could draw this like. Okay, same compounds, yeah. This is more of a perspective. I mean, we still see that. Okay, how about the next one? Why don't you do that one on your own? Below is more of those where you need to, okay, this is sort of pulling it all together, guys. There was more on the previous page. More of them to do here. Perhaps on Wednesday we'll do the one in the pink in class. Okay, we need to do that, go over that last bit there. E and F. Please work on that. That this week, yeah? No? Class on Wednesday, but that's it? Okay, alkyne chemistry, next handout. We'll begin alkyne chemistry on Wednesday. Have a good day, guys.